Welcome for the session. In this class, we will be seeing what are the different mathematical modeling for electromechanical systems. Before that, let us see what is electromechanical systems. An electromechanical system is one which is having the electrical systems as well as mechanical systems. These two systems are integrated in electromechanical systems. Let us see the sum of electromechanical systems used in control engineering. So, number one is armature control DC motor, field control DC motor, number three is tachometer, number four is amplifier, number five is generator and solenoid. These are the basic electromechanical systems which is used frequently in control engineering. Let us see the definition of each one. First, I will take armature control DC motor. An armature control DC motor is an electromechanical system wherein the speed of DC motor is controlled using armature supply voltage while field supply voltage remains constant. This is a definition for armature control DC motor. An armature control DC motor is an electromechanical system where the speed of DC motor is controlled by armature supply voltage while field supply voltage remains constant. Here, whatever the torque generated due to the motor is directly proportional to armature supply voltage. So here we will be writing IA of T, but IF of T is constant. Field supply voltage remains constant. When you want to energize a motor in order to get rotation, there are two things. One is you can excite armature supply voltage or else you can excite field supply voltage. Whenever we take up the derivation or mathematical modeling of armature control DC motor, you will be seeing two circuits. So the torque will be equal to Kt into Ia of T, where T is the torque generated in the motor, Kt is constant of proportionality or torque constant, Ia of T is armature current. Next, field control DC motor. A field control DC motor is an electromechanical system. The speed of DC motor is controlled using field supply voltage while armature supply voltage remains constant. So here the excitation is only made for field supply, not for armature, but there is a constant armature current flowing across the circuit. So the torque will be directly proportional to field current and torque will be equal to Kt into If of T, where T is the torque, Kt is torque constant, If of T is armature field supply current. Field supply current. Here armature voltage is constant. So next, number three is tachometer. Tachometer, already you know, it is a speed measuring device. A tachometer is an electromechanical system where the speed of DC motor is directly proportional to the voltage. So here simply what we can say is tachometer is directly proportional to torque or voltage is directly proportional to angular velocity. That is the equation for tachometer. So the rotation is based on torque here. What directly we will write Kt into omega. Omega is d theta by dt, Kt into d theta by dt. This is the equation for tachometer. Then amplifier. Amplifier, as you know, It is an electromechanical system which amplifies the input voltage. So output voltage is directly proportional to input voltage. Output voltage will be equal to Ka into input voltage, where Ea naught of t is output voltage, Ea of t is input voltage, Ka is constant of proportionality called as amplifier constant. This is the equation for amplifier. Next, generator. So generator is a device, again the torque will be generated in terms of highest torque, because the generator need to have a more torque in order to rotate the component. The shaft will be very big and the shaft will have more weight. We need to overcome the more inertia. So the torque is directly proportional to generator current. Generator current is nothing but simply we can call it as field current. So torque will be equal to kg into field current or generator current, where kg is nothing but the torque constant or it is a generator constant. Then solenoid. Solenoid is an electromechanical system where the force is directly proportional to the rate of change of angular displacement, or the force is directly proportional to current. Generally what happens is, when a core is wounded with a coil, apply some voltage, then there will be a force generated. This force will push us the coil in and out. So this is a coil and this is a wounding. This is a core and this is a wounding. Whenever you pass electricity, because of Lorentz force, it will tend to move and it will apply some force. That force is directly proportional to the current which is induced here. So F is equal to K into IF of t, or I of t just simply, where K is the constant of proportionality which is called as solenoid constant, F is the force, I is the current. In some of the cases what happens, because of rotation of armature, the armature will be rotating continuously because of inertia effect. There will be a electromotive force which is generated in the armature, which will turn the motor, which will tries to turn the motor in reverse direction. That is nothing but back EMF. It is a resistance offer for the voltage. So back EMF VB, back EMF will be opposing the motion, so which is directly proportional to d theta by dt. And this, if you take a proportionality constant, you will get Kb into d theta by dt, where Kb is called as back EMF constant. So these are the 6 important electromechanical systems you will be using in control engineering. But as per your syllabus, the derivation will be done for only these two, armature and field controlled DC motor. Let us recall the definition. Armature controlled DC motor is an electromechanical system in which the speed of the DC motor is controlled using armature supply voltage while field supply voltage remains constant. Field controlled DC motor is an electromechanical system in which the speed of the DC motor is controlled using field supply voltage while armature voltage remains constant. Tachometer is a device where the torque is directly proportional to rate of change of angular displacement. Amplifier is the device which tries to amplify the input voltage. So this is the expression for amplifier. Generator is a device where the torque is directly proportional to the generator current or a field current. Solenoid is a device when a coil is wounded with the wires, or when a core is wounded with a coil, the electricity is passed. Because of this electricity, the force will be generated which will be moving the core in to and fro. That is nothing but solenoid, where F is directly proportional to the current across the circuit. And back EMF will be there in almost all the armatures, because this back EMF will oppose the rotation motion, and this back EMF is directly proportional to rate of change of angular displacement, and Vb is equal to Kb into d theta by dt, where Kb is constant of proportionality called as back EMF constant. You have to remember the torque for armature controlled DC motor, you have to remember the torque for field controlled DC motor, and you have to remember what is the back EMF, because the back EMF derivation will be included in armature controlled DC motor. Derive an expression for armature controlled DC motor considering back EMF. So for that you need to remember the torque equation, you need to remember the back EMF equation. So in the next class we will be doing what is armature control DC motor and field control DC motor. So in the previous class we have discussed mathematical modeling of physical systems. We have discussed mathematical modeling of mechanical systems including translation and rotation. Also we discussed mathematical modeling of electrical systems along with the circuit. Whenever it is a mechanical systems, we will be introducing Newton's second law of motion, summation of forces is equal to mass into acceleration. If you are using electrical systems, Kirchhoff's voltage law, the total voltage across the circuit will be equal to sum of the individual voltage across their elements. So, let us see the mathematical modeling of electromechanical systems. Electromechanical systems are the systems which are the combinations of both electrical as well as mechanical systems. Here, electrical systems and mechanical systems are integrated. Example for this is fan. The output of the fan is rotation and input of the fan is electrical voltage. Here, this is an electromagnetic mechanical systems wherein it is having both electrical as well as mechanical system incorporated into it. In electromechanical systems, you have two derivations. One is regarding armature controlled DC motor and another one is field controlled DC motor. Let us see what is the mathematical modeling for armature controlled DC motor. As per the definition of electromechanical systems, armature controlled DC motor is an electromechanical systems in which the speed of DC motor is controlled by armature supply voltage while field supply voltage remains constant. Here the excitation of torque is based on armature supply voltage but the field supply voltage remains constant. Hence the name, it is armature controlled DC motor. I will write the circuit. So this is a typical circuit for armature controlled DC motor which is having resistance RA, armature resistance, and inductance LA, armature inductance, and let VA of T be the voltage across the armature current or armature. So simply we can say this VA of T is armature supply voltage. Here field supply voltage remains constant. So what I will do is this field current, I will make this as a constant because it is an armature controlled DC motor. So this armature will have some of the electromotive force which is caused due to the rotation of motor. Since the motor has an inertia, during the rotation there will be a negative force EMF generated which will be turning opposite to that. That is called as back EMF. We will call it as V suffix B. And because of excitation of armature voltage, we will be getting a torque, and this torque will be rotating the motor. The torque generated is nothing but T and the rotation is theta, and let I be the mass moment of inertia of the torque, and there is some amount of damping that is called as C. So this is a mechanical system and this is an electrical system. While excitation of armature supply voltage, we will be getting a torque in the mechanical systems. So this is armature controlled DC motor. So what basically I will do is I will be mathematically model what is the armature controlled DC motor with respect to field supply voltage as well as the rotation. Let us see how to model this. So the first thing is, since it is an electrical network, I will solve for electrical network, apply Kirchhoff's voltage law to the circuit. This is the first thing. If I apply Kirchhoff's voltage law, the armature voltage will be equal to voltage across resistance, voltage across inductance, and voltage across armature or back EMF, that is called a VB. Voltage across resistance is resistance into current. So I will call it as RA into IA of T, where IA of T is armature current, plus voltage across inductance is L into di by dt. So LA dia by dt, and voltage across back EMF is nothing but it is KB, constant of proportionality of back EMF or back EMF constant, into d theta by dt. So you will be generating back EMF because of rotation of armature. So this is the equation what we will get. So here we need to find out what is the current across the circuit. In order to find out current across the circuit, we will be using a mechanical system as well as the basic definition of armature current. So this I will call it as equation number 1. As per definition, armature controlled DC motor is a electromechanical systems in which the speed of DC motor is controlled by using armature supply voltage while field supply voltage remains constant. Mathematically, the torque is directly proportional to armature current. If I take the proportionality constant, I will get torque will be equal to KT into IA of T. This is a equation of torque based on armature supply voltage, and this I will call it as A. The torque is also induced in mechanical systems. If I consider the mechanical systems, again I will get the equation for the torque. Now I will consider mechanical system. So mechanical system, this is I will write the free body diagram. Free body diagram is a diagram which represents the forces acting on the system. I will be locating theta, angular displacement. In the same direction, the torque will be acting. So the direction of external torque and rotation will be the same. In order to restore this, what we will do is the damping torque will be generating reverse of the theta and T. Here T and theta will be generating in clockwise direction, but C theta will be generating in counterclockwise direction. So C theta dot is the damping torque. So this is a free body diagram of the mechanical system, and I will apply Newton's second law of motion. So according to Newton's second law of motion, Newton's second law of motion states that the summation of torque will be equal to I into alpha in rotational systems, as you studied in the previous sessions. Summation of F is equal to ma, where the equivalent terms for force is torque, equivalent term for mass moment of inertia is phi, equivalent term for acceleration is angular acceleration alpha. So I alpha, I will start from I theta double dot. You have to start from mass. I theta double dot will be equal to T. So the forces which are acting in the direction of theta will be taken as positive. The forces or torques acting opposite to direction of theta will be taken as negative. So here the T will be acting in the direction of theta, hence that torque is taken as positive, minus C theta will be acting opposite to theta, it is taken as negative. I will rearrange this. Torque will be equal to I theta double dot plus C theta dot. So this is the second equation. I will call it as equation B for the torque. What I will do is I will equate the definition of armature controlled DC motor as well as the torque in physical system. So from A and B, I will get I theta double dot plus C theta dot will be equal to KT into IA of T. So I will rearrange this. I need the value of IA of T. So IA of T will be equal to 1 by KT I theta double dot plus C theta dot. So this is the equation for armature current. So this I will call it as equation 2. I will be substituting the value of IA of T in equation 1. So substitute IA of T in 1. So in other words, substitute the equation 2 in 1. So VA of T will be equal to RA, KT is constant. I will be taking out that RA by KT into I theta double dot plus C theta dot plus LA divided by again KT is constant I theta double dot plus C theta dot plus the back EMF KB into d theta by dt. After obtaining this, the voltage equation is in terms of angular rotation. The concept is we need to evolve a mathematical model. The mathematical model is nothing but a transfer function. The transfer function, it is the ratio of Laplace transformation of output variable to Laplace transformation of input variable under the initial condition 0. Here what we will do is the output variable is theta, that is the rotation of motor, and input variable is voltage across armature, that is VA of T. We have written the expression in terms of input and output quantity. Now it is ready to obtain the final output model. So for this equation I need to apply Laplace transformation. So apply Laplace transformation. What we will get? VA of T will be VA of S. So the time domain is changed to frequency domain. That will be equal to RA by KT constant. If I apply Laplace transformation for theta double dot, it will be S square into theta of S. So IS square into theta of S plus C theta dot is S into theta of S. So IS square plus CS into theta of S plus I have taken theta of S as a common in both the terms, hence theta of S as written only one time, then LA. So here a common mistake will be done by the students while writing this I theta double dot plus C theta dot is we will be forgetting to write d by dt. That is very important thing. Usually this mistake will be happen during the flow. So please look this term and write corresponding d by dA. So here you have to write d by dt. Later you will realize that you have missed S term. So very important. Often these mistakes will be there in all the cases. Up to here you will be solving. In the substitution you will be doing this mistake. You will be missing d by dt because you will be copying I theta double dot plus C theta dot here itself by looking this equation. So please look this equation. This mistake is common, hence you put a star here so that mistake should not be done in your exams. LA, d by dt is there. This d by dt is S. So if you apply Laplace transformation, differential equation will be converted to S divided by KT into again the same term you copy IS square plus CS into theta of S plus the final term Kb, it is a back EMF constant, Kb into, since d by dt is there, it is S into theta of S. So this is the deduced form of circuit or the equation after applying the Laplace transformation, but still it has to be simplified. For the simplification itself you will get the marks. So what I will do is VA of S, left hand side I will take that common. Here I will take IS square plus CS into theta of S as a common. If I take this as a common, theta of S I will be writing later. So if this term is common, RA plus LA into S, theta of S. So 1 by x, it is like this, so it will be 1 by x. So KT will be in denominator plus KB into S into theta of S. Again, I will be simplifying this equation. So VA of S will be equal to IS square plus CS into RA plus LA into S. I will simplify this, plus KB into KT into S. This KT will be going this side into theta of S divided by KT. What is the equation I want? I want the Laplace transformation of output variable. Laplace transformation of output variable is theta of S, and Laplace transformation of input variable, this is VA of S. So this is a mathematical model. Just reverse this, it will be equal to KT divided by IS square plus CS into RA plus LA into S plus KB into KT into S. So this is a final equation or a final model for the armature controlled DC motor. This is a final equation considering the effect of back EMF. Here we have taken back EMF effect. So basically what we have done is we have written the circuit. In the exam they won't give any circuit, just they will ask derive an expression for armature controlled DC motor. When they ask that, you have to write the definition. First you have to write an armature controlled DC motor is an electromechanical systems in which the speed of DC motor is controlled using armature supply voltage while field supply voltage remains constant. This is a definition and you have to write this equation. The torque is directly proportional to armature current and torque is equal to KT into IA of T, where T is the torque, IA of T is armature current, and KT is constant of proportionality of armature controlled DC motor, or it is a torque constant. After deducing this, apply KVL to the circuit, then the input voltage will be equal to voltage across each terms, voltage across resistance, voltage across inductance, voltage across back EMF. So only three things. After this you will get an equation. In that equation substitute voltage across resistance, R into IA, voltage across inductance, L into di by dt, and voltage across back EMF, Kb into d theta by dt. In some of the times they will mention the notations EB or Ka like that. For the given expression you solve. If it is not mentioned, directly take Kb into d theta by dt. Instead of d theta by dt, they can give omega. That is also correct. Omega is nothing but angular displacement, angular velocity, which is given by rate of change of angular displacement. Omega is equal to d theta by dt. This also they can ask. Instead of that, they will give just omega. Omega equal to d theta by dt. Once if you deduce this expression, you have to calculate what is the armature current value. What is IA of T? IA of T you will be calculating using the torque equation. This is a torque equation, and using the mechanical systems. You will be writing the free body diagram while applying the Newton's second law of motion. You will be getting the equation of the torque. The equation of torques are compared and you will get the equation for armature current. That's all. Very easy step. After that, simplification. While simplification, you will be often forgetting d by dt term in inductance. So please careful, s term will be there in inductance. So this is a substitution. After applying the Laplace transformation, you will get this. After that, you have to simplify, you have to get what is the output and what is the input. Here the output is rotation and input is armature supply voltage. So there are different cases here. First, I will be neglecting the back EMF. If I neglect back EMF, VB will be 0. If VB is equal to 0 means this term will not exist. This term will not exist, and KB into KT into S will be 0. So the equation will be theta of S divided by VA of S will be equal to KT divided by IS square plus CS into RA plus LA into S. So this is the equation if you neglect the back EMF. There is another case if you neglect back EMF, and inductance. So if you neglect back EMF, voltage across back EMF will be 0. If you neglect inductance, voltage across inductance will be equal to 0. So in this equation, this term and this term will be 0. The total voltage of armature will be equal to only the voltage across the resistance. So the final equation will be theta of S divided by VA of S will be equal to KT IS square plus CS into RA. So these are the different cases in armature controlled DC motor. Similarly, we need to derive an expression for field controlled DC motor. Let us see what is the concept of field controlled DC motor. So in the previous session, we discussed armature controlled DC motor. Let us derive an expression for field controlled DC motor. Before that, let us recall the definition of field controlled DC motor. A field controlled DC motor is one in which the speed of DC motor is controlled by using field supply voltage while armature supply voltage remains constant. This is a definition of field controlled DC motor. In the field controlled DC motor, whatever the torque is generated, which is directly proportional to field supply voltage. So in the case of armature, the torque is directly proportional to armature current, whereas in field control, the torque is directly proportional to field current. So let us write the circuit of field controlled DC motor. So RF is the resistance across field current and LF is resistance across a field motor, we can call it as. Then an armature. So here in field current there is no back EMF. Since we are exciting an external resistance, that is field current, there will be no back EMF generated in the field current. The advantage of field current is whenever we want to rotate a motor for a long duration and the motor will have large amount of inertia forces, then we will excite field supply voltage. For a smaller powers, armature supply voltage. So here another thing is current across armature remains constant. Very important thing. So here the excitation is only based on a field supply voltage. And again, because of this excitation, torque will be generated. Because of torque, the motor will get rotated and it is having a system, rotational system along with a damping. So let us derive the expression for output and input of field control DC motor. So this is Vf of T, field supply voltage. First I will apply KVL, Kirchhoff's voltage law, for the circuit. The Kirchhoff voltage law, the input voltage, the input field voltage will be equal to voltage across resistance and voltage across inductance of the field. So there is no back EMF here, be careful. What is the voltage across resistance? It is simply RF into IF of T. Voltage across inductance is LF into DIF by dt. So this is field supply voltage. This I will call it as equation number 1. As per definition of field control DC motor, the torque is directly proportional to field current. If you remove the proportionality constant, you will get torque constant into IF of T. So this is the equation for the torque. This I will call it as A. The same thing what we have deduced in armature control DC motor, the same expressions we are using here. Then I will consider a mechanical systems. So mechanical system is this one. This is I. Then torque T and theta. In order to restore this, we will be using damping torque, which is C theta dot. So the damping torque will be acting opposite direction to the angular displacement. So if I apply Newton's second law of motion, summation of torque will be equal to I into alpha. I is I into theta double dot will be equal to the torques which are acting in the direction of theta will be taken as positive. The torque which are acting opposite to direction of theta will be taken as negative. So torque minus torque will be acting in the direction of theta, hence it is positive. C theta dot will be acting opposite to the direction of theta, hence it is negative. So what is the torque in this equation? The torque will be equal to I theta double dot plus C theta dot. So this is an expression of torque using mechanical systems. So this I will call it as A and this I will call it as B. I will be comparing A and B. Comparing A and B, what we get? We get K, what is T? KT into IF of T will be equal to I theta double dot plus C theta dot. So what is KT? It is a constant of proportionality of the torque, which is field torque. What we need? IF of T will be equal to 1 by KT I theta double dot plus C theta dot. So this is an expression for field current, which I will call it as equation number 2. I will be replacing the value of IF of T in 1. So I will be equating the value of field current in equation 1. What I will get? So Vf of T will be equal to RF divided by KT into I theta double dot plus C theta dot plus LF by KT into d by dt of I theta double dot plus C theta dot. So remember, please, d by dt, very important term. Now I will apply Laplace transformation. Then what I will get is Vf of T will be equal to RF divided by KT into I theta double dot plus C theta dot plus, so since I have applied Laplace transformation, theta double dot changes to S square and theta dot changes to S into theta of S plus the same thing LF by KT, this d by dt will be S, it is IS square plus CS into theta of S. Again theta double dot S into theta of S, since d by dt terms are twice, it will be S square into theta of S. For this, S into theta of S. In both the terms, what I will do is, I will take theta of S as a common, then I will get that expression. So, Vf of t changes to Vf of S, since I have applied Laplace transformation. Vf of S will be equal to Rf plus Lf into S into Is square plus Cs into theta of S divided by Kt. So what I want is output rotation divided by input field. Theta of S is the output, Vf of S is the input. That will be equal to Kt divided by Rf plus Lf into S into Is square plus Cs. So this is a mathematical model or the transfer function for field controlled DC motor. Again, what we have done basically, first we started with the circuit, we have applied Kirchhoff voltage law to the circuit. The input voltage will be equal to voltage across resistance and inductance of the field. So that you have written, as per the definition, the torque is directly proportional to field current, that we have written torque will be equal to Kt into If of t. Then after that, considered the mechanical system. This is a mechanical systems. In the mechanical systems, we deduce the expression of the torque by writing the free body diagram of the mass with respect to torque and C. So we have deduced the torque. What is the torque across the I, T and theta? What is the opposite restoring torque? It is C theta dot. So then after that we got an expression for torque here. This torque and this torque are compared. It will be Kt into If of t into I theta double dot plus C theta dot. After that we got an expression for field current. That field current is substituted in the equation 1 in the equation of voltage. After that we applied Laplace transformation for the circuit. T domain changes to S domain and theta changes to theta of S. Theta dot changes to S into theta of S, theta double dot changes to S square into theta of S as per the Laplace transformation conventions. So after that I got a common terms, the common terms has been taken. The definition of Laplace, the definition of transfer function is the Laplace transformation of output variable to the Laplace transformation of input variable. Laplace transformation of output variable is rotation. It is a mechanical system. Laplace transformation of the input variable is voltage. It is an electrical system. Hence, it is called as electromechanical systems. So, we have got a transfer function theta of S by Vf of S. This is the expression. So, speaking straightly, for the armature controlled DC motor, if you replace A with F, it is a field controlled DC motor. But remember, in the field controlled DC motor, there will be no back EMF, since we are exciting the field coils of the motor. So the field coil is excited, because of that you are getting the rotation of the motor. So this is about field controlled DC motor. Thank you.